Now, the circuit that I've drawn on the board here, this is called an RL circuit. It doesn't have a capacitor in it. It only has a resistor and an inductor. And so, of course, if we give some values to this, I'm going to say that I have a voltage here of 200 volts. I'm going to say that I have an inductance of 5, and the unit of inductance is called a Henry. Okay? And then I'm going to say that I have 50 ohms of resistance here. And out of those three terms that I could get for voltage, okay, I've got resistive voltage, which is current multiplied by resistance. And I've got inductive voltage, which is inductance and dIdt. And my total voltage, my voltage that I'm producing here is 200. This is, again, your book does this, which is why I've done that. Sometimes it's written as a battery like that. Be 200 volts, that's what I wrote a minute ago. So those two added together along with this one, I'll just say at the source, whatever battery it may be, in this case is 200. Those have to add up to 0. So I've got I times 50 plus L, which is 5, dIdt equals 200. Now, why do I write it that way? Well, these are eating up the voltage. So if you want to add these all up, you'd say I've got 200, I've got minus IR, and I've got minus L dIdt. I've just written it like this. The source is on one side, and the things that are eating up that voltage are on the other side. And what I see here is, this looks not unlike what we were just messing with before. We've got dIdt, 5 plus 50I equals 200. Now there's a variety of things we can do here. One of the things we can do in this particular case is we could divide through by 5 because it makes the equations look easier, okay? But what do I have? I have I with respect to t, derivative of I with respect to t. I've got an additional term that has I in it, and then I've got a constant on that side. Even though it's not at all like the compartmental analysis problem, the differential equation itself is like that. Because what do I have? I've got I, I've got a function of I, or I've got the derivative of I, I've got a function of I here, which means that this other piece is what I'm going to use to get my integrating factor, right? Because that term, then, e to the integral of whatever's in front of the I, which is 10. It could be a function of t right there, but it's not. And one of the tricky things here we're talking about dIdt. The last one we're talking about dx dt, etc. So this I is a function of t, okay, we're taking the derivative of that. This other term that's sitting out there may be a function of I, okay? We don't know. But in this case, it's just 10. It could have been, okay? In this case, it's just 10. So we do the integral of 10 dt. That integrates to e to the 10t. This is my integrating factor. Multiply times e to the 10t. And as is the case anytime we do this integrating factor thing, what we have right here, well, this is, I have I e to the 10t, where I have held the first, taken the derivative of the second, plus held the second, taking the derivative of the first. So that entire thing is the derivative with respect to t of that product. I can now separate variables. Got the differential of this product equal to 40 e to the 10t dt. I'm going to integrate here. I e to the 10t equals 40, and that thing e to the 10t. And what we've seen when we had e to the t over 50, we generated 1/5, or we generated 50. Here we're going to generate a 1/10. You can do the u substitution if you don't believe me, but that's what will happen. apologize for the lack of board space. But I have that equation down there. I now can divide by e to the 10t. I'm going to be left with I on the left-hand side. On the right-hand side, if I divide by e to the 10t, that's going to go away, and I've got just 4 plus, and then I've got c over e to the 10t, or c e to the minus 10t, depending on how I want to look at it. In this particular example, what I'm going to say is I'm going to say at the beginning of this time, the current was 0, okay? So I got to switch somewhere here, and I say, I'm going to push that button down. And once I push that button down, current is going to begin flowing here. But up until that point, it won't, because the positives from here can't get anywhere. The positives from here want to go all the way around and get to the negatives from here. That's what they want to do. When they see a path to do that, they will. Otherwise, they're just a battery and they just sit there. But when I close that switch, at time 0, I of 0 is equal to 0. There's no current flowing. Therefore, when I look at this equation here, I say, well, I equals 4 plus c e to the 0 is just 1. 0 equals that. C is minus 4. Therefore, my total current as a function of time is 4 minus 4 e to the minus 10t.